Good day and welcome. My name is Scott Shipp, and this is Defense Infrastructure Capital Project Optimization. This is a review of a project that I completed as part of my capstone project for my master's degree in Applied Business Analytics. The question that this presentation will cover is, what does it look like when we apply an optimization model to infrastructure projects? This presentation is broken down into three parts. At the beginning, I will provide an introduction to linear programming and integer programming. So these two types of programming are the tool that was used to help optimize our capital investment plan. With that introduction in place, I'll then review the model data that was used to create this optimization, and lastly, we'll compare the results. So the first question is, what is linear programming? And linear programming is simply a mathematical method of finding an optimal solution given a set of inputs. And every linear programming problem has three parts, and we'll look at each of them in turn, and those are the objective statement, decision variables, and constraints. The objective function describes the problem that you are trying to solve, and generally there are three types of problems, either to maximize profits, reduce costs, or to achieve a specific target. The second part of a linear programming model are decision variables. These are the aspects of the model that you can influence or control. So the question is, what decisions can I make or must I make? The third part of the linear programming model are the constraints. These are the factors that must be considered. So are there minimum or maximum amounts that affect either the decision variables or the objective function? Or are some solutions out of bounds? For example, if there is a budget as a constraint, the solution cannot consume more budget than is available. We'll now look at a linear programming example so you can see how the system works. So we'll have an imaginary company that makes two products, product A and product B. Each of these products produces a certain amount of profit. But each of these products also require different amounts of raw materials and production time to create. So the question for the company is, how many units of A and B should the company make to maximize their profit? So here is our objective function. The objective function is to maximize the profit. This is described mathematically simply as the maximum profit is equal to the profit of unit A times the quantity of unit A plus the profit of unit B times the quantity of unit B. The decision variables are how much of each product to make. And lastly, we have the constraints. As described before, both A and B require different amounts of raw materials and time to produce. And our constraints require that there be a total amount of time and a total amount of raw materials to consume to produce those units. This is called linear programming because we can plot the solutions to the problems in a line. We can see here that on the y-axis shows how many units of product A we can make, and on the x-axis it describes the number of units of product B that we can make. The red and green line indicate the constraints. So constraint 1 would be the resources constraint, and that shows that we could either make 50 of A and 0 of B to a maximum of 30 B and 0 A. The constraint 2, the green line, is the time constraint, and you see how that can limit what can be made. Once those constraints are put in, we see that we are left with a blue shaded region called the feasible region. Any spot in there will provide a solution that satisfies the constraints, but the most profitable mix is going to be on one of the four corner points. And we can see here that the intersection of constraint 1 and constraint 2 is probably going to be the best solution. This would indicate that we're going to be making approximately 28 item B and maybe about 18 or so of item A. A slight variation of linear programming is something called integer programming. They're very similar, the exception being, instead of being a line, we're dealing with whole numbers. The analytic project that I'm going to present uses the variation of integer programming where the decision variables are binary. So instead of describing a quantity of something to produce, we're going to have a series of things that are either a yes or a no answer rather than an amount. As an example, our objective function here can be to maximize a profit, where the profit is based on the sum of all of the profits from the projects that are selected. Our decision variables are a series of projects, and the question is whether or not each or any of these projects will be funded. Our constraint in this hypothetical scenario is a total available budget to fund the projects. Now on to our defense infrastructure case study. The data set for this project was the consolidated demand list. This list had 194 projects with a total estimated cost of $7.9 billion. Each project had an estimated cost as well as a priority score. Now, the current decision selection process rank orders the projects by priority score, which means the highest prioritized projects will get funded first. If we assume a $300 million budget for these projects, only the first 4 projects which have the highest priority scores get funded. A key assumption that I made was to reinterpret the meaning of the priority score. For the purpose of this project, the priority score represents how much risk is eliminated from the portfolio by funding that project. So the goal of this analysis is to determine what is the maximum amount of risk that can be reduced from the portfolio given that same $300 million budget. The idea for this analysis came from looking at a scatter plot of all of these projects. So on the y-axis, we have all of the funding requirements for the projects, and on the x-axis, we have the priority scores. And what I saw here is that there are many relatively high priority projects at a low cost. So this is how the optimization case study was set up. The objective function was to maximize the priority score, which is based on the sum of all of the priority scores from all of the projects that are selected. The decision variables in this model include all 194 projects. The question is whether or not the model will choose a project or not. The constraints are the total available budget, and each project has to be selected in full or not at all. What the model does is it goes through all of the decision variables and iterates different mixes of selected projects to figure out which one provides the maximum score for the budget. Now here are the results. Under the current method, with a $300 million budget, 4 projects are selected with a total priority score of 3,790. With the optimization model, 33 projects are selected with a total score of 17,253. What we should realize here, though, is that none of the 4 projects that are the 4 highest priority projects were included in the 33 projects that were selected in the optimized version. In conclusion, this video reviewed a project that I completed as part of my master's in applied business analytics. I introduced the concepts of linear and integer programming and how they can be used to support decision-making. Specifically, I demonstrated how these optimization tools can be applied to defense infrastructure decision-making. Lastly, if we redefine the purpose of our capital investments to reduce risk rather than to prioritize, we'll receive a different set of investment decisions. If you have any questions, you know where to reach me. Thank you for listening.